Chapter 10, looking at the topic of gases. We're going to cover gases in 3 different class periods with the different divisions shown here. When it comes to gases, uh, there's something that you're going to have some prior knowledge of. In middle school, in high school, you would have looked at the topic of gases. Molecular orbital theory, not so much. So this is returning to something that you probably have some experience with, and we'll build on that. On this slide, I show 3 different sets of questions to consider the characteristics of a gas. At the top left, the question is a gas more likely described as a homogeneous mixture or an inhomogeneous? Are there strong attractions or weak attractions? Is it mostly empty space or mostly particles? So when you think of a gas, for each of these, is the description best described as something from the left-hand side or something from the right-hand side? So make your choices for each of these and compare with a classmate. Similarly, does a gas have mass? Suppose we took a balloon and filled it up with helium. Would the mass increase, decrease, or remain unchanged? And then finally, what's happening at the particle level? So we have a container that has liquid water, and if a zoomed in particle level representation is shown, what if the same container now holds evaporated water? Which of these particle level descriptions would be the best match? Take a second, compare your answers, and we'll discuss. For the first question, we think of gas as being a homogeneous mixture with weak attractions between the particles. There's a lot of empty space. The gas itself can be easily compressed, and there's unrestricted particle motion as the gas particles are free to move about. If we add helium to the balloon, the mass is going to increase. Now, the balloon will then float, and the point here is we need to have a distinction between the density of the object and its mass. So if we're adding particles, we're definitely increasing the mass, but the density is going down. In this last picture here, this particle level representation is best. So when we go from the liquid to the gas, we're still keeping the molecules intact of H2O. They're just separating apart from each other. So the spatial orientation is different. A few elements are found as gases at ordinary temperature and pressure. We've seen several of these. Our noble gases, helium, neon, argon, etc., are monatomic gases. We've also encountered diatomic ones. Hydrogen gas, nitrogen gas, oxygen, fluorine, chlorine. Those are all diatomics that we've memorized. This table lists quite a few other common compounds that are found as gases at room temperature. Notice how these are all molecular compounds. They're composed entirely of nonmetals. They have a simple molecular formula and a low molar mass. Nearly every gas we encounter is going to be a molecule in this class. Now, why are these gases? Key is going to be this description of them having a low molar mass. That's something we're going to look at in Chapter 11. So for properties of a gas, we've said that a gas will have mass. We can also think about its volume, pressure, density, and temperature. So pressure, that's defined the same way we'd have it in a physics class, the force divided by the area. We'll often be encountering units for the atmospheric pressure, or the symbol ATM. For conversions involving pressure, 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 760 torr. We want to be able to convert between atmospheres, millimeters of mercury, and torr. This description of 760 millimeters of mercury, the first barometer was made by putting some mercury into a tube that was open at one end, sealed at the top. It was inverted, so it was turned over and put into a pool of mercury. The height of that column of mercury then is 760 millimeters. That's the definition here of how we have millimeters of mercury related to units of torr. And it's being held upward because the atmospheric pressure is pushing down on the mercury that's remaining in the pool down here. So suppose a gas has a pressure of 785 torr. What would be its pressure in atmosphere? So grab a calculating device, figure that out for me. We're going to be doing calculations in class today. So if 760 torr is 1 atmosphere, if you have 785 torr, it's a little bit more than 1 atmosphere. I calculated 1.03 atmospheres equaled 785 torr. Let's consider this scenario. Let's say we have gas in a balloon, where a balloon is a flexible container. How is that connected to pressure? Let's see if we can answer this. The pressure inside a balloon is different from the pressure outside of the balloon. Under what conditions? If it's on Mount Everest, if it's undergoing a volume increase, it's filled with helium, or the pressure can never be the same inside and outside the balloon. Take a moment, discuss this. Let's compare ideas. The best answer here is when it is undergoing a volume increase. If we have a flexible container, if the pressure inside is not the same as the pressure outside, the flexible container then will change its volume. That is an indication for us that the pressure is not equal both inside and outside of the container. This is something we need to try to visualize. So if we were to take a balloon and we think about we have particles of gas inside exerting a force from inside the balloon, if that force is the same as what's acting outside of the balloon, then the volume of it doesn't change. But if the forces are different, the balloon can either increase or decrease in volume. Now, I've brought up several terms like pressure, volume. There's going to be relationships between the pressure, the volume, the number of moles of gas, and the temperature. When we're thinking pressure, the symbol is going to be P and will often be in units of atmosphere. Volume, symbol V in liters. Number of moles of gas is given the symbol N. The temperature is given symbol capital T. We're often going to be using that now in degrees Kelvin. That was something that was introduced way back in chapter 1, but now we're going to begin to use it. So we need to know a conversion between Celsius and Kelvin. The size of the degree is the same in both scales. They're just offset. 0 degrees Celsius is 273.15 Kelvin. So given a Celsius value, we can add 273.15 to it to turn it into a Kelvin value. We also are going to encounter what's called standard temperature and pressure, or abbreviated STP. That's describing a pressure of 1 atmosphere and a temperature of 273.15 Kelvin. Now, there's various relationships between the pressure and the volume, or maybe the temperature and the volume, or the temperature and the pressure. I'll bet you're familiar with some of these relationships. So what I'd like you to do is to consider how might we be able to explore these. These are the resources we have on hand. We've got some balloons. We've got liquid nitrogen, which is quite cold. It's at 77 Kelvin. And we have a vacuum pump. With a vacuum pump, it's able to evacuate, remove the air from what's inside what's called a bell jar here. So take a second, check with a classmate. Do you know of relationships between things like the pressure and the volume for a gas? And how could the resources I list on the screen here be used to explore them? Try to propose some experiments. So here I show an image of the vacuum pump and a bell jar. So we have a balloon that's being placed within the bell jar. Now this is before the vacuum pump's been turned on. Make a prediction. What's going to happen to the balloon as the air is evacuated from this chamber? Let's check it out with this video. We have the sealed balloon. The bell jar goes over the top of it. Vacuum pump is being turned on. What are your observations? Does this match what your prediction was? going to stop it right there and then releases it so that air goes back into the chamber. So the volume of the balloon clearly increased. Why did that happen? How can we explain that in terms of the different terms that we have? Well, the pressure outside of the balloon was reduced because we removed the particles of air from the chamber. That meant that the pressure inside of the balloon and outside of the balloon were no longer equal. The pressure was greater inside of the balloon. The force inside of the balloon was greater than the forces on the outside, and the volume then increased. The volume of the balloon increases, and the pressure of the balloon inside the balloon decreases in that process. This is telling us that the relationship between the pressure and the volume is proportional to some constant value. The pressure and the volume have an inverse relationship. When one goes up, the other one goes down. That's what's being plotted here. If we want a linear relationship, we could do the pressure and 1 over the volume. That would give us a linear relationship. But the pressure and the volume themselves have an inverse relationship. Let's consider the other resource. We have liquid nitrogen, which is at 77 Kelvin. Make a prediction for me. What's going to happen if we take a sealed balloon and we immerse it in liquid nitrogen? And even more, how might we explain that? Why does it happen? Check with a classmate. Here's our video. Sealed balloon in a puddle of liquid nitrogen. What are we observing? I see that the volume of the balloon is decreasing. Decreases until it becomes rigid. Why did that happen? Why did the volume of the balloon decrease when it became colder? The temperature inside the balloon decreased. The force inside the balloon was less than the force acting outside of the balloon. The pressure inside was less than the pressure outside. Because the pressures are not equal, the volume changes. The volume is decreasing until the forces are once again equal. This is telling us that there is a direct relationship between the volume and the temperature. And in fact, this is one way that the temperature scale for Kelvin was established. The pressure and the volume are proportional to the temperature. If the temperature goes down, the volume goes down. Or if the temperature goes down, the pressure inside the vessel goes down. If you were to take those and hypothetically extend them, as the temperature gets smaller, the volume's decreasing, hypothetically it would reach some minimum value. I say hypothetically because it's going to turn from a gas to a liquid or to a solid before then. But notice how they would all extend down to the same point, this negative 273 degrees Celsius. This is why we're going to have to use the Kelvin scale. We want to make it so we don't have any negative values when we're looking at the temperature in our calculations, so we're going to use the Kelvin scale instead of the Celsius scale. Now, the pressure and the volume was proportional to the temperature. I'd say the pressure and the volume is also proportional to the amount of gas. If you take a balloon and you add more air to it, the volume is getting bigger and bigger. The volume was getting bigger and bigger because when we added more of the particles to it, the pressure inside was greater than the pressure outside, so we saw this expansion. The ideal gas equation now summarizes these different relationships, where the pressure and the volume we saw being proportional to the amount of gas, N, and the temperature. If we want to make it equal instead of proportional, we use a constant. So this constant is our gas constant. It has a value of 0.08206 liter atmosphere per mole K. This will be given to us on an exam, and this points out why we need to have our volume in liters, our pressure in atmospheres, number of moles, and then the temperature in Kelvin. If we have all of those, then we have an R value consistent with that. Now, an ideal gas, that's a hypothetical gas that this equation works for. Okay? We're going to look later on in the chapter at examples when it's not applicable, but for now, we're going to look at scenarios where it is. And remember when we were describing standard temperature and pressure, that was 0 degrees Celsius, which is 273.15 Kelvin, in 1 atmosphere. We're going to be using that information, our gas constant, and the ideal gas equation for some calculations. Now, what would be the volume of an ideal gas at these conditions of standard temperature and pressure? Standard temperature and pressure, remember, was 1 atmosphere and 0 degrees Celsius. So we have 3 different scenarios where different amounts of gas, 4 grams of helium gas, 28 grams of N2, and 16 grams of CH4 were put into containers. Those values were chosen because if you have 4 grams of helium, if we use the molar mass, that would be 1 mole of helium. 28 grams of N2 is 1 mole. 16 grams of CH4 is also 1 mole. So for all of these, we could put them into our equation PV equals nRT. We see our scenario here where we're solving for the volume, but we have it under standard temperature and pressure, so it was 1 atmosphere and 273.15 Kelvin. In all of those, if we solve for it, we get the same volume, 22.4 liters. This is a value that might be useful for us in other calculations. Notice it is the number of molecules here, not their mass, that determines the pressure. In all 3 of these scenarios, at standard temperature and pressure, we have used 1 mole of gas. 1 mole of gas at standard temperature and pressure occupies this volume of 22.4 liters when it's behaving ideally. We're going to explore and consider why this is later in the chapter. Now, the gases themselves can still be different. Take a moment, rank these gases in terms of density. Helium, nitrogen gas, and the CH4. They are all occupying the same volume. Does that mean they all have the same density? Here would be my ranking. We have the same number of particles, but they have a different mass. Helium has the smallest mass, the N2 has the largest molar mass. So they have the same number of particles, but different mass, and in that volume, that would lead to a different density. So here, let's work through a few typical gas calculations where we're using our equation PV equals nRT. Some of these we can use the values directly, and others require unit conversions. So here's 4 different calculations we can work through. The TA in your room is going to divide you up. Give one or more of these a try, and then I'll show my work. Here's my work for the first calculation. So we have a pretty simple scenario where we're considering our PV equals nRT. We're adding some helium gas to a 5-liter container, and we want to know at what temperature would the pressure exceed 20 atmospheres. This is how I set up my work for these. I write the equation PV equals nRT, and then I just draw arrows to connect what I know. In this case, I knew the pressure, I knew the volume, I have my gas constant, I converted grams to moles for the helium, and I have the last value that I was looking for. And that's what I would solve. I write the expression like this, and that's how I end up solving it, because I can see spatially all the different terms that I have, and I do my conversions here on the outside. How about this one? Calculate the number of molecules in a deep breath of air whose volume's listed there with the temperature and the pressure. Again, I would set it up this way where I write PV equals nRT. It's 735 torr, so we can divide by 760 to turn that into atmospheres. I need it to be in atmospheres because that's what my R value is. I'm converting the temperature into Kelvin. All of those terms, I want them to be consistent with each other. I need to be in Kelvin. I need to be in atmospheres in order to make the R value work. I solve for N, and that's how many moles I have of the air. Now, air is a combination of nitrogen gas, oxygen gas, and a few others, but it doesn't matter what they are in terms of their identity when we're looking at the number that they have. A gas is just a gas when we're using PV equals nRT. We're going to connect PV equals nRT to stoichiometry, a topic we loved back from chapter 3. So here's a scenario given. When in chapter 3, we could convert between grams and moles by using the molar mass. In chapter 4, we found how we could use concentration and volume to get to number of moles. Same kind of thing, but now we can see how we can solve for number of moles by using a description of the gas in terms of PV equals nRT. That's what's going on here. So we have a reaction that was given. We see in our balanced equation 1 mole of calcium carbonate gives me 1 mole of CO2. We can do a calculation to see how many moles of calcium carbonate based on its molar mass were involved. That would also then be how many moles of the carbon dioxide gas at standard temperature and pressure. So the question really then is to calculate the volume, given that many number of moles. We could use PV equals nRT, same setup that I've had to figure out what the missing value would be. Or we could return to that relationship where at STP, 1 mole of a gas occupies 22.4 liters, and just set up a simple proportion to figure out what the volume is. Both of approaches lead us to the same answer. The last one here is a little bit different, connecting the topic of density to the ideal gas equation. We know that the ideal equation is PV equals nRT, and the density is defined as the mass over the volume. We could begin to bring those together by manipulating it to see a ratio of the number of particles we have, the number of moles divided by the volume. And if we know not just the number of moles, but what their molar mass is, this is a way we can begin to think about the density. At the bottom here, a really typical question. What's the density of N2 gas given 130 degrees Celsius and 750 torr? And we want to report that in grams per liter. Now, nitrogen gas, if I look at the periodic table, is 28 grams per mole. If I look at this now in relationship to PV equals nRT, I see a pressure value listed, R is a constant, the temperature's value is listed. It looks like I have two variables. I have both the volume and the number of moles of gas. So in order to answer this, we're just going to assume we have 1 liter. If we're going to be reporting it in grams per liter anyways, let's just assume we have 1 liter in our calculation. Now we're just down to one variable. So I'd set this up the same way I've been setting up the other ones. We know the pressure, the volume. We'll convert from Celsius to Kelvin. We got our gas constant. So we can first of all solve for the number of moles of N2. And then given the number of moles of N2, use the molar mass to figure out how many grams that is. So it's a two-parter. We would first figure out the number of moles, assuming a volume of 1 liter. And then second, we can convert that to grams. If you want more practice, the ideas that we've discussed here in this video, we have some applications of PV equals nRT listed at the end of the chapter. We have ones involving density of gases, and definitely practice some where we connect it back to the stoichiometry.